SUID and SGID executables. As a quick recap from earlier in the course, SUID files get executed with the privileges of the file owner, while SGID files get executed with the privileges of the file group. If the file is owned by root, it gets executed with root privileges, and we may be able to use it to escalate privileges. We can use the following find command to locate files with the SUID or SGID bits set. To explain what this command is doing, it will search for items recursively from the system root directory, only matching files which either have the SUID or SGID bit set. And then it will run the ls-l command against each one. As you can see, by default there are a number of SUID and SGID files on Linux systems. Usually none of these are exploitable. Just as we were able to use shell escape sequences with programs running via sudo, we can do the same with SUID and SGID files. A list of programs with their shell escape sequences can be found at the GTFO-bins website. Refer to the previous section on shell escape sequences for how to use them. A quick word on LD preload and LD library path. You may be thinking, why can't we just use the same LD preload and LD library path environment variable tricks we used with sudo privilege escalation? Well, by default, this is disabled in Linux due to the obvious security risk it presents. Both these environment variables get ignored when SUID files are executed. Certain programs install SUID files to aid their operation. Just as services which run as root can have vulnerabilities we can exploit for a root shell, so too can these SUID files. Exploits can be found using Searchsploit, Google, and GitHub, in the same way we find exploits for kernels and services. Let's run the Linux Smart Enumeration script. In the results, we can see that there is an uncommon setuid binary, which is for the exim mail transfer agent. Exim is somewhat notorious for having security vulnerabilities, so it is always worth looking into for privilege escalation. If we want to find this binary manually, we can use this find command. And here we see the exim binary in the results. The version of exim is rather obvious from the file name, but we can confirm it by executing the file with the -- version option. On our local machine, we can use the Searchsploit command to see if this specific version is vulnerable. It looks like there is a single privilege escalation for this version. Remember, if your search doesn't return anything, try removing version numbers or using Google and GitHub. I've transferred the exploit code over from our local machine. If we execute it, we get a strange error from bash. Note the $M symbol. This usually means that the exploit code was written using Windows new line characters. Luckily, we can remove the offending characters using a simple sed command. To get a $M symbol, simply hold Ctrl, press V, and then M. Now simply execute the script to spawn a root shell. When a program is executed, it will try to load the shared objects it requires. By using a program called strace, we can track these system calls and determine whether any shared objects were not found. If we can write to the location the program tries to open, we can create a shared object and spawn a root shell when it is loaded. Let's run the Linux Smart Enumeration script with the levels set to 1. In the results, we can see a number of files with the SUID bit set. Again, we can find these manually using the following find command. Let's take a closer look at the SUID-SO file. First, we'll try executing it. It seems to just be performing some calculation. Let's use the strace command to see what's happening when we execute the file. There's a lot of data here, so let's pipe strace through grep and match some specific keywords. Now, this just means that any errors will get redirected to standard output, so that grep will match them as well. We want grep to just output lines that match either open, or access, or the string no such file. The results show us that the executable tries to load a number of shared objects. However, some cannot be found. Notably, the executable is trying to load the libcalc.so file from our user's home directory. If we were to create this file, we could inject code into the process and spawn a root shell. First, we need to create the .config directory in our user's home directory. I'll change to the .config directory as well. Next, we need to create a file, libcalc.c, and give it the following contents, which should just spawn a shell when loaded. Now we're going to compile libcalc.c into libcalc.so. Finally, we execute the SUID-SO executable and gain a root shell. The path environment variable contains a list of directories where the shell should try to find programs. If a program tries to execute another program, but only specifies the program name rather than its full absolute path, the shell will search the path directories until it is found. Since a user has full control over their path variable, we can tell the shell to first look for programs in a directory we can write to. If a program tries to execute another program, the name of that program is likely embedded in the executable file as a string. We can run strings on the executable file to find strings of characters. We can also use strace to see how the program is executing. Another program called ltrace may also be of use. Here you can see how to run strings, strace, and ltrace against a file or command. If we use find to locate all SUID and SGID files on the Debian VM, we see that the SUID-env file should execute with root permissions. If we execute the file, we see that it appears to try and start the Apache web server. By running strings against this file, it appears that the file may be trying to run the service command to do this. We can confirm this using strace. Notice that the service command is being executed via a shell, which also inherits our user's environment variables. Since the service command does not use an absolute path, we can create our own version of the service executable and prepend its location to the path variable, which will cause the shell to use it and execute it with root privileges. I've created a file called service.c in my current directory with the following contents, which simply spawns a shell when executed. Now we just need to compile service.c into an executable called service. Finally, in the same command, we need to prepend our current directory to the path variable and execute the SUID-env file, which should get a root shell. In some shells, notably bash versions lower than 4.2-048, it is possible to define user functions with an absolute path name. These functions can be exported so that subprocesses have access to them, and the functions can take precedence over the actual executable being called. If we use find to locate all SUID and SGID files on the Debian VM, we can see that the SUID-env2 file should execute with root permissions. If we execute the file, we see it appears to try and start the Apache web server. By running the strings command against the file, it appears that the file may be trying to run the service command to do this, however this time with an absolute path. We can again confirm this using strace. Ordinarily, this would only be exploitable if we could write to the /user/sbin/service file. However, if we check the version of the /bin/sh shell, we can see that it is bash version 4.1.5. Versions of bash lower than 4.2-048 allow us to define bash functions with forward slashes in their names. These functions then take precedence over any executables with an identical path. Let's create a function with the name /user/sbin/service and make it execute bash. Now we need to export the function. Finally, we again execute the SUID-env2 file, which in turn executes our function and spawns a root shell. Bash has a debugging mode which can be enabled with the -x command line option, or by modifying the shellops environment variable to include xtrace. By default, shellops is read-only. However, the env command allows shellops to be set. When in debugging mode, Bash uses the environment variable ps4 to display an extra prompt for debug statements. This variable can include an embedded command which will execute every time it is shown. If an SUID file runs another program via bash, e.g. by using system, these environment variables can be inherited. If an SUID file is being executed, this command will execute with the privileges of the file owner. In bash versions 4.4 and above, the ps4 environment variable is not inherited by shells running as root. We use find to locate all SUID and SGID files on the Debian VM. We see that the SUID-env2 file should execute with root permissions. If we execute the file, we see that it appears to try and start the Apache web server. By running strace, we see that the service executable is used to do this, and it runs in a shell with our user's environment variables. If we check the version of the /bin/sh shell, we see that it is bash version 4.1.5. Versions of bash lower than 4.4 inherit the ps4 environment variable when running as root. The ps4 environment variable is used to display the prompt while bash's debugging mode is on. Let's run the SUID-env2 file in a modified environment, where bash's debugging mode is enabled. And we'll set the ps4 variable to some value. We can see that it is prepended to each line of output. Since this is bash, we can use command substitution to execute a command and display the result. We see that the whoami command was executed, and it was executed as root. If we use this command execution to create a root bash SUID file, we can use it to gain a root shell.